So,
all right, so I guess you can see my slides and I can also click. All right, yeah, thanks Salman for the introduction and thanks for the invitation to this seminar. So today I will talk about essentially some results of Valentin's master thesis, who used to be a master student in Cologne. And yeah, kind of the title of the talk is Wigner's theorem for stabilizer states, and it's joint work with Valentin and David Gross, who's my PhD supervisor, and one of my two PhD supervisors. And kind of the results are all there, and hopefully kind of the paper we are writing right now is soon on the archive. Yeah, by the way, if you have any questions, just interrupt me and ask or write in the chat. Maybe Salman, you can monitor the chat a little bit if I don't see it, and then I can just refer the questions to me. All right, so what's going to be the outline of the talk? So first of all, I will talk about the classical Wigner theorem, which is somewhat related to symmetries of quantum states and quantum mechanics. Then I will talk about symmetries of stabilizer states. Stabilizer states are just a subset of all quantum states. And then, yeah, kind of our result is to characterize these symmetries, and then I will talk about some potential applications and some outlook. Okay, so first of all, let me just quickly talk about symmetries in general. So why should we care about symmetries in general? They played a major role in several groundbreaking discoveries in math and physics. For example, Einstein's model of general relativity is related to physics. Well, don't ask me any questions about this. I kind of copied this. I wanted to have a physical motivation. I'm a mathematician by education. Like for me, what's interesting about symmetries is in general. So if you want to study some object, then symmetries really might help you to understand it better. And on the picture, what you can see is a projection of the E8 root system. So you can see it's a very highly symmetric object. The E8 root system is a system of vectors living in dimension 8. And I think, as far as I know, it doesn't have any relations to quantum physics. But this is a super highly symmetric object that you can fully describe just by its symmetries. And yeah, it was used to construct. So this root system comes with a lattice, and this was used to construct optimal sphere packings in dimension 8. So sphere packing is a way of arranging spheres in space such that they do not overlap. So it's kind of in 3D, it's kind of, you just take balls, maybe cannonballs, and you want to store them in a way such that they take as few space as possible. And this was used to construct an optimal sphere packing in dimension 8. And yeah, recently Marina Vyazovska got the Fields Medal for proving that this configuration gives an optimal sphere packing. And what you can see here, you have a lot of symmetries. So yeah, symmetries are kind of important and nice things to study. All right, so let us get more to quantum stuff. So yeah, what are symmetries of a quantum system? And over time, there's been developed a lot of different ways to define symmetries. And traditionally, people considered Wigner symmetries. And what are Wigner symmetries? So if we consider Wigner symmetries, then we take pure states, and we want to map pure states to pure states. So in this case, we have these rank 1 projectors psi, and psi is supposed to map to some psi prime, another rank 1 projector. And these this map should preserve transition probabilities. So if I take the inner product of the images, psi prime and phi prime of psi and phi, and I square the inner product, then it's supposed to be the same as the inner product of psi and phi. And yeah, if I illustrate kind of, for example, all 1 qubit quantum states, then I can just parameterize them by this block ball here. And now all pure states are just on the boundary of this block ball, so they are kind of a 2-dimensional sphere. And now, yeah, Wigner symmetries are just all rotations and reflections of this sphere. So essentially, it's the orthogonal group acting on this sphere. And now, yeah, the classical Wigner theorem says the following. It says that every Wigner symmetry of the state space is given by a conjugation of unitary or anti-unitary matrix. So every symmetry that satisfies this property here is given in this way. So I just conjugate my rank 1 projector psi, ket bra psi with u, and then kind of, yeah, every symmetry is given by this way. Okay, so now let us generalize this idea of symmetries and let us introduce some other notions of symmetry. So we fix some subset Q of the space of in the space of Hermitian matrices over some Hilbert space H. So yeah, H could be, for example, C2, and then Q could be, for example, the set of all quantum states. And now, what are Wigner symmetries in a more general way? Wigner symmetries are a bijection W from this set Q to Q, such that the trace is preserved. So if I take the trace of Q1 and Q2, which are two elements in Q, then the product, the trace of that product is the same as if I apply the map W to Q1 and Q2, and yeah, then this is equal. And you can really show that this is essentially the same notion that we've seen on this slide before. Now just apply to density matrices or Hermitian matrices. Well, another notion of symmetries are Kadison symmetries. These are bijections of the convex hull of this set Q that we're considering here. And these symmetries satisfy a certain linearity or affine condition. So yeah, if I take the convex hull, then I get something that's connected where I can add things. So here this Q might be finite, but here I have some set that's connected in space where I can add things up. And now Kadison symmetry is a symmetry that is linear under convex combinations. So if I add these two elements and I scale them with some p, which is between 0 and 1, then k commutes with these linear combinations, and then I'll get a Kadison symmetry. And I can also like easily extend this notion to the span of Q, and then this is essentially just a normal linearity of a function. And then there's a third notion of symmetry that we will consider in this talk, and these are anti-linear Hilbert space symmetries. So these are symmetries that are induced by actual symmetries on the Hilbert space. So again, H is a map that maps my set Q to Q. And if I take an element of this set Q, like small q, then this kind of the symmetry acts by conjugation by some operator L. So I just map Q to L, Q, L inverse, and L inverse is some anti-linear map on H. Now, for example, if Q is the set of all quantum states, now written down as density matrices, then Wigner's theorem tells us that these three classes are isomorphic. Well, in general, these classes are not the same, but there's a certain type of inclusion that you can see here on the picture. Yeah, now the question to you, like, is there someone who can tell me like which type of symmetry is now contained in which type of symmetry? So either you're very good with like faces of famous mathematicians and physicists, or you were super fast with definitions and can just infer how the inclusions have to look like after seeing the definitions. Well, I guess it's a pretty hard question. So
I mean, the only one I don't know is Kadison, and he's the picture on the right then, because the other two, it's Hilbert and Wigner in the middle, right?
Yeah, precisely. Very nice. Very nice. So yeah, Hilbert is on the left, Kadison is Wigner in the middle, and Kadison is on the right. Yeah, very nice. Oh, nice, nice. I didn't expect anyone to solve this way. So exactly, these are the type of inclusions. So Hilbert space symmetries are contained in the set of Wigner symmetries, and this is contained in the set of Kadison symmetries. Maybe like a short proof why every Hilbert space symmetry is a Wigner symmetry. So if H is some Hilbert space symmetry, and I want to show that it's a Wigner space symmetry, then I have to show that inner products are preserved. So if I plug in Q1 into my Hilbert space symmetry and I compute the trace, then by definition my Hilbert space symmetry has this form of conjugation. And then, well, this inner part here just vanishes. The trace is cyclic, so I can just like take this L1 inverse to the front, and then this vanishes as well, and then I see that inner products are preserved. If you want to show that Wigner symmetries are also Kadison symmetries, first of all, there's a small subtlety that Wigner symmetries are just like defined on certain sets, but you can extend them linearly to the span of these kind of finite sets. And then it's also just a one-line proof to show this. Well, if you're asking about, for example, when the converse directions hold, so when are Kadison symmetries, so when we have equality in these cases, we will see some examples during the talk when we have equality in these cases. Okay. So now let me get to symmetries of stabilizer states. Okay, yeah. Let me briefly mention our main result, and then we will just dig deeper in how to derive this result and what it actually means. So let me fix some notation. First of all, we fix stabilizer states. So stabilizer states are essentially states on Hilbert space level. You can define them as n qubit states over z to the d. Z to the d, so d is just usually some prime power. So it can be 2, but it can also be some other prime. And these are usually like rank 1 projectors that you can see here. And sometimes there will be a little ambiguity, so sometimes I will also just refer to the vectors in Hilbert space as stabilizer states. And these states, they define a polytope, and this polytope is usually called the stabilizer polytope for 1 qubit. So for d equals 2 and n equals 1, kind of the rank 1 projectors are so like the rank 1 stabilizer states are exactly kind of these 6 vertices here. And the stabilizer polytope is this octahedron, so all that contains all convex combinations of these 6 points within the Bloch sphere. And now what we want to study is, we want to study the Kadison or linear symmetries of these objects, or affine symmetries, but essentially these things are the same. Now, our main result is that we can classify them for, well, any interesting, or what means interesting, but for any cases where, for any n, and for any d where d is a prime power. So for 1 qudit, or 1 qubit, these symmetries are isomorphic to the Reth product of the symmetric group on d letters with the symmetric group on d+1 letters. So SD here really refers to the group of permutations of n symbols to itself. For n qubits, the symmetries are given by the extended Clifford group. So this is not new, this result. This was proven by Markus Heinrich, who was a former PhD student of David, I think in 2019 or something like this. And kind of our like really new contribution is that for n qudits, so when d is some prime power and d is not 2, then the symmetries are isomorphic to a group which is called the group of affine symplectic similitudes, which has a very fancy name. I'll slightly explain what this means in the sequel of the talk. And one other thing that you can show easily is that all these symmetries, so I said we want to study Kadison symmetries. We've seen this picture of inclusions. Wigner symmetries were a subset of Kadison symmetries. But you can show that in this case, Kadison symmetries and Wigner symmetries coincide. All right. So now let me get to kind of the first case, to stabilizer states with 1 qubit. So we've already seen that these 6 stabilizer states are kind of their rank 1 projectors are the vertices, these 6 points, and these are kind of 6 points on the Bloch sphere. And if I want to write them down as Hilbert space vectors, these are exactly these 6 vectors. And now what we want to do is we want to study Kadison or Wigner symmetries of these 6 vectors. And how can we do this? We can do this in the following way. So these 6 vectors, we can subdivide these 6 vectors into 3 bases. These 3 bases, they're all orthonormal. So if I compute the inner product of 2 of these vectors, it's going to be 0. And if I compute the inner product of one vector of, say, b1 and b2, and I square it, then I obtain something like 1 over 2. And this can be generalized. So if I consider kind of 1 qudit, then I'll in some sense, I could just generalize this construction. So like 1 qudit stabilizer states, they can be decomposed. They can be written as a disjoint union of d+1 orthonormal bases of c to the d. So all the elements within the basis are orthogonal. And if I take like an element of bi and bj, and I and j are not the same, and I compute their inner product squared, then this is 1 over d. So if you plug in just 2 for d here in this case, then this boils down to the 1 qubit case here. And kind of this special structure helps us to classify symmetries in this case. So how do we do this? Let us first start with Wigner symmetries. So Wigner symmetries now are just a symmetry that map kind of these stabilizer states to stabilizer states, and they are supposed to preserve inner products. So this should hold for my symmetry. And I've seen that for the case d equals 2, I had these 3 bases, and these were all my stabilizer states. So I want to find a map that maps these 6 states to themselves and preserves inner products. And yeah, now I can easily see that every symmetry is specified by exactly 2 things. So what can I do? I can just like permute elements in one of these orthonormal bases. So I can just like exchange like 1, 0 and 0, 1, for example. What else can I do? I can just take like the basis b1 and map the elements of the basis b1 to the elements in the basis of b2. This gives me a symmetry, and these symmetries, they will all kind of preserve the inner product. What a thing that I cannot do, for example, is I cannot take the vector 1, 0 and map the vector 1, 0 to one element in B2 and map the vector 0, 1 to an element in the orthonormal basis B3. Because if I did this, then I would violate this inner product rule that I have here. So this tells me that every Wigner symmetry in this case is given by the choice of one permutation of S2 for these three sets by permuting its elements, and then I have one permutation that permutes these bases. So this is then a symmetry. Then this is an S3 symmetry. So now I can just like permute these three bases here. And in general, for one qudit, what's the group that realizes this? This group is exactly the Rath product of the symmetric group SD and SD plus 1. So now I just replaced the 2 by a D. And now here you can see a picture of like a typical Advent Rath that's very typical, that you can typically see in Germany during Christmas time. And maybe I guess this, so if you want to understand this group operation, it somehow alludes to the structure of a Rath. So yeah.
It's also interesting, I think. Also interesting, I think that in the English language, Rath is mostly associated with death, whereas in the German language, it's associated with Christmas. And so I think, yeah.
Yeah, but I checked, I Googled this several times, and I checked for a translation of Adventskranz, which is the German word. And the proper translation I found was Advent Wrath. I don't know how common Advent Wraths are in the UK or.
No, I don't think it's really known so far, but yeah, indeed, when we use wrath, we do not think of death. And so I want everybody to be happy and, share our association of festivities and not death.
Good. All right. Are there any other questions, comments? Good. Then let me continue. So right now we just studied Kadison's Wigner symmetries of one qudit stabilizer states. But as I said, actually we want to study Kadison or linear symmetries of these sets. So we want to study symmetries that map the convex hull of the stabilizer states that we've seen to the convex hull of stabilizer states. And they should satisfy, this type of linearity condition where this, is supposed to be a convex combination. But as I said, I can also kind of extend this whole thing to this span of the set of stabilizer states. So we want to study these type of symmetries. Before we studied Wigner symmetries, we had this kind of chain of inclusions. Hilbert space symmetries are a subset of Wigner symmetries, are a subset of Kadison symmetries. But there's one nice thing. So there's a certain sufficient condition for Kadison symmetries to be equal to Wigner symmetries. And this is the following. Whenever my set that is supposed to be mapped to itself is a complex projective 2 design, I'll just consider like complex projective 2 design as a black box here, then Wigner symmetries coincide with Kadison symmetries. So if you want to get an intuition what complex projective 2 designs are, let's say it's kind of a set of like nicely distributed states in the space of pure states. And yeah, you can also replace these two by higher orders. And in general, so this property holds for every set of D+1 mutually unbiased bases. So every set that had this structure that you can decompose it into D+1 orthonormal bases, such that if I take two elements of two different bases and I compute the inner product squared, then it's 1 over D. However, in this case, we have an example where like Wigner and Kadison symmetries do not coincide with Hilbert space symmetries. So the symmetries that I have here, I cannot write them as so they are not induced by some linear or antilinear map on the Hilbert space. Well, essentially what this implies is the following. So if I apply one of these symmetries to the whole state space and I consider its image, then it's not going to be the state space. So it's going to map the state space to something else. All right. Now we've considered one qubit and one qudit. So let's continue with n qubits. This is not a new result. It's hidden in the appendix of a paper written by Markus and David, which is called The Robustness of Magic and Symmetries of the Stabilizer Polytope. So you can see it already in the title, but the symmetries were characterized somewhere in the appendix. And in order to give the result, we have to define some kind of very prominent objects in quantum information and quantum computation. So first of all, we need the n-qubit Pauli matrices. These are just n-fold tensor products of the typical 2 times 2 Pauli matrices I, X, Y, and Z. And then what else do we need? We need the Clifford group. And the Clifford group are all 2 to the n unitary matrices that map Pauli matrices to itself. So if I can associate a group to the set of Pauli matrices, then the Clifford group is essentially just, well, in group theoretic terms, just the normalizer of the Pauli, the unitary normalizer of the Pauli group. So yeah, I need Clifford unitaries, and the other thing I need is transposition. Yeah, transposition is just the map that maps A to A transposed. So it just kind of exchanges rows and columns of a matrix. So this is not complex conjugation. And what I can do is I can implement transposition by complex conjugation with an anti-unitary matrix. And this matrix C implements complex conjugation with a computational basis. So this is really an anti-unitary matrix. And if I have these 2 objects, then I can define yeah, all symmetries of n-qubit stabilizer states. And now the linear symmetries of like the stabilizer polytope or n-qubit stabilizer states are is just the group generated by transposition and the Clifford group. And sometimes this, or usually this group is also called the extended Clifford group. Yeah, here you have to be a little bit careful. So so here the Clifford group acts by conjugation on your stabilizer states. So if your stabilizer state is some density matrix, so then I conjugate this matrix with the Clifford unitary and then obtain another stabilizer states. So here the consequence is the following. Well, in contrast to the general one qudit case, here all symmetries are also Hilbert space symmetries. So every symmetry I can write it down as conjugation by some unitary or anti-unitary matrix. And there's also a high-level reason for this. And the high-level reason in this case is that qubit stabilizer states form a complex projective 3 design. So they're even like better distributed than like general qudit stabilizer states. And whenever I have this property, then Kadison symmetries and Wigner symmetries coincide, or just coincide with Hilbert space symmetries. Yeah, so in fact, there's kind of an intermediate group of symmetries to prove this result. These are Jordan symmetries, maybe you've heard of them. And essentially what you can show is that if you have a complex projective 3 design, then yeah, every Kadison symmetry is a Jordan symmetry, and then if you have a Jordan symmetry that preserves inner product, then you can show that that it comes from a Hilbert space symmetry.
And I have a quick question. So you think of SP here as a polytope, right?
Yeah.
One can also ask about the combinatorial symmetries of the polytope, right? So those permutations of the vertices that preserve the phase relations.
Yes, in this case, I guess you just get the same symmetries. Because, oh, well, so for one qudit, you get the same. So for one qudit, combinatorial symmetries of the phase lattice are just the symmetries, are just the same as the linear symmetries. It's a good question whether this is also the case if I don't consider one qudit but several qudits. It's in fact, okay, I guess the problem here is that we don't really know the phase lattice of the stabilizer polytope. So if you don't know the phase lattice of the stabilizer polytope, it's pretty hard to study its combinatorial symmetries. So I don't know if there's an abstract reason how you can, well, to show that in fact the symmetries of the phase lattice, the combinatorial symmetries of the phase lattice coincide with all linear symmetries without knowing the actual phase lattice. But I guess, yeah, this is...
So I think it's a very good question, and I don't know the answer, and it's a bit dangerous because the paper has been kind of like 90% done since a few months now, and it's very bad to, you know, suggest new good questions to ask because it could mean it takes even longer if we also want to look at. So I have to kind of force myself not to think about it too hard. But it could be, and I don't know whether it's true or not, it could be that the combinatorial structure is in fact determined by the geometry. Yeah, so kind of like lying within the same basis, you can express geometrically as being orthogonal, right? And maybe likewise, you can somehow, you know, one can argue that even though we don't know the precise combinatorial structure, it is a function of geometrical data. I have an old paper like 15 years ago or something where we did this with the PR boxes. there we could, you know, at some point it was open, what is the symmetries of PR boxes? And there we could argue that combinatorial data was fixed by geometry, and then we could classify it this way. So maybe there's hope, but I don't know, and it's a very good question.
David, I have a follow-up question. So the PR boxes that you mentioned, what is the polytope exactly? Is it the bipartite Bell scenario, the CHSH, or are you just
so it was a multipartite PR boxes, right? And it is, and so the way they are introduced is via duality. So you have the primal object, and the primal object are conjugate local measurements. And so you assume you can only do tensor product measurements, right? And so you got these measurement operators, and then you take the state space to just be the polar dual of that. Right, so it's like the biggest state space that is consistent with, you know, two complementary local bases and no entangled measurements. You know, that is the definition. And I don't know, you know, the resulting polytope, whether like this dual thing, whether it has, whether it can be identified as some classical object. I don't know, but maybe. No, I'm sorry, I don't know. You know, we could ask Valentin again, because, you know, he identified some of the polytopes that, you know, we already knew, but I don't know what the answer is.
I mean,
okay, thank you. Yeah,
sure.
Sounds good.
So at least in the one qubit case, you can show that combinatorial symmetries coincide with these linear symmetries. But well, maybe Valentin knows. Well, I mean, it's kind of what Valentin did, but I think there we really exploited that we know the structure of the phase lattice. Yeah, so I see him nodding. So yeah, so this was the correct answer. Okay. So now let's get to several qudits. So in order to define several, like the symmetry group for several qudits, we just generalize kind of the stuff that we saw on the slide before. So first of all, we generalize the Pauli matrices, and therefore we generalize the Pauli X and the Pauli Z matrix. So in general, the Pauli X matrix kind of acts by translation, so it takes kind of the qth computational basis vector and maps it to the q plus 1th computational basis vector, and yeah, Z, that maps q to omega to the power of q times q, and omega is simply a dth root of unity, and q is some number and z to the d. So these operators act on z to the d. And now kind of you can, well, if you just plug in like 2 in these equations, then you just obtain kind of the normal Pauli X and Z operator. And now you can define the general Pauli matrices based on these 2 operators. And usually they are labeled by 2 strings, A and B. These strings are just like A1 up to AN and B1 up to BN that you can see in the exponents here. And then you simply tensor kind of X and Z operators together, you multiply them, and you take like certain powers of them that are given by these A1s and these AIs and BAs. And these AIs and BAs are just numbers in ZD. And then you equip the whole thing with a phase that is simply, that depends on the inner product and this number, tau here, to the power of this product. And now we've already seen that transposition gives us a symmetry in the case of n qubits. And so if I want to like model transposition within the spaces, then what does it do? It takes such an operator and maps this operator TAB to some operator TA minus B. And so what it does, it multiplies this number B by some factor -1. -1, I can also see -1 as an element of the group ZD. And now I can just generalize this. I can just say, I do the same thing for some number alpha. And then this operator TAB is mapped to some operator TA alpha B. And what you can show is that this gives you a stabilizer symmetry. Maybe as an idea, so if you know a little bit more about how to construct stabilizer states usually come as sets of maximally commuting operators of this form. And then you can show whenever you write down a maximally commuting set of Pauli operators and you apply this operation to this set, then you will just obtain another set of maximally commuting Pauli operators. And this gives you a symmetry. And now our result is that all linear symmetries of the stabilizer polytope are given by the Clifford group. So the Clifford group now is the normalizer of this set of generalized Paulis. this action that comes from this number alpha. And then you can show that this group is isomorphic to the group of affine symplectic similitudes of this space ZD to the 2n. Maybe like to see the connection, so these vectors A and B, they live in ZD to the n. So if I take the triple, then it lives in this space. And yeah, this way, using this whole phase space formalism, you can formulate this result also a little bit differently. But in order to see the generalization, I think this is kind of the best way to see it. All right. Yeah, so maybe two short comments on this result. So in the case of D being a prime power, stabilizer states form a complex projective 2 design. So again, all symmetries are also Wigner symmetries. So Kadison and Wigner coincide for this case as well. But in this case, not all the symmetries are Hilbert space symmetries. However, what you can do is the following. So you can implement them on a subspace of your Hilbert space. So if your vectors live on a subfield of Z, so if the entries live on a subfield of Z, I think it's kind of the cyclotomic field, then you can somewhat relate these symmetries to elements that act on the Hilbert space. But in general, these are not Hilbert space symmetries. Okay, yeah. Now let me talk about some potential applications, or are there any more questions? All right, so let me talk about some applications. Kind of the first application is the lambda polytope, or the structure of the lambda polytope. Yeah, let me define the lambda polytope. It's simply the set of all, it's a subset of all Hermitian matrices over the space ZD tensor n that have trace 1, and the inner product with stabilizer states is lower bounded by 0 for all stabilizer states. If I consider the one qubit picture, I have the following picture. So this is the stabilizer polytope. Now the set lambda 1, 2 is exactly this cube here. So I was so free to copy this picture from one of Jen's papers. I hope this is okay. And yeah, so in some sense, like this is a polytope, and lambda is also a polytope. And usually polytopes come with a dual polytope, and within the space of matrices of trace 1, this is precisely the definition of the dual polytope of the stabilizer polytope. Okay, well, this is kind of an object that has been studied by Gian and Michael Zorel and Robert Rausendorf, and also by them and me together, and I also studied this in my master thesis. There's some interesting insights, and these are the following. So first of all, this object is in some sense stable under Pauli measurements on conjugation by Clifford unitaries. So what does this mean? So whenever I take a point within this cube here, it does not need to be a quantum state. So here we have the Bloch field, but it can also be, for example, a vertex of this cube. And I apply measurements to this point and I normalize, then I will get another operator that has trace 1 again, and then this operator will be contained in this cube. And if I conjugate, for example, A00 by a Clifford unitary, then I will obtain another point within this cube. And the other insight is that this set is a polytope. So it's the dual stabilizer polytope in some sense. And what happens if I apply this concept of duality to polytopes, then it flips inclusion. So here I have kind of my polytope and I have the quantum state space. I know the quantum state space is self-dual. And now if I dualize this polytope, then I will obtain a polytope that contains all quantum states. So yeah, this is a polytope that contains all quantum states. And what I can do right now is the following. I can use this object lambda to classically simulate quantum computation with magic states. So in quantum computation with magic states, kind of your two main operations are Pauli measurements and Clifford unitaries. Now I have an object that is stable under these things. Then I can derive a Monte Carlo type simulation algorithm to simulate quantum computation with magic states, which is kind of a universal model for quantum computation. And essentially what this means is, so if I take some quantum state within the state space, so within this sphere in this example, then I can write it down as a convex combination of the vertices of the polytope lambda. And then I can sample one of these vertices and I can just kind of simulate the evolution of this vertex under Pauli measurements and Clifford unitaries. Okay, so yeah, that's kind of a way to classically simulate quantum computation with magic states that was kind of developed by Michael, Gian, and Roberts. But there are some drawbacks about this idea. And kind of the major drawback is the following. So I know the set that is here described as a set of linear inequalities. I know it's a polytope, but I don't know the vertices alpha I. And yeah, this is kind of bad news. I only know the vertices for some cases. So I know the vertices for one qudit. I know the vertices for one qubit, and we know the vertices for two qubits. We know some. Yeah, I think Michael ran a lot of numerical simulations to get more vertices for 3 and 4 qubits and also for 2 qudits. We know some infinite families of vertices for arbitrary dimension. Yeah, this was kind of something that I did in my master thesis, and also Gian, Michael, and Robert did. But we don't have a full list. And now kind of, well, one hope is that, yeah, that symmetries might help to find more of these vertices. And how can we do this? Kind of the key observation is the following. If I have a linear symmetry of the stabilizer polytope, then the symmetry coincides with the symmetry of the polytope lambda and d. Simply because if I have a polytope and its dual polytope, then they have the same linear symmetry group. So I think if I refer to Gian's question, I'm not sure if this also applies to the, well, no, it also completely applies to the combinatorial symmetry group. Yeah, so there kind of the combinatorial symmetries are also the same. And now what's the consequence of this? So if I have some vertex of the polytope lambda and d, for example A00 here, and I have a symmetry of the stabilizer polytope, then if I apply this symmetry to alpha, then I obtain another vertex of lambda. So for example, if A00 is my vertex and I apply some symmetry of the stabilizer polytope, then I might end up in the vertex A11. But I will never end up in some point that lies outside the cube or inside the cube. So it will always be a vertex. Or I will also not end up somewhere on the boundary, but really exactly in the vertices. Yeah, but there are also more bad news. So I mean, now we have this result. We know some families of vertices and also potential vertices for qudits. But if we apply kind of all symmetries to them, then we obtain nothing else that we haven't known before. Yeah, so here maybe one open question that I will also mention in the end is, yeah, it would be nice to have to know some vertices and well, some maybe odd-looking vertices, and if we apply kind of symmetries to the vertices, do we get other interesting vertices that we haven't known before? Yeah, second application is a little bit more vague and something that, well, could be investigated further in. And this is, yeah, how to exploit symmetries in convex optimization problems. So yeah, it's just going to be kind of, so I mean, I'm trying to convey a more general idea here that is not necessarily related to stabilizer symmetries. Could also be seen like a motivation why to study symmetries in general. So suppose you have some linear optimization problem, for example. So you want to maximize this function trace x, which is linear, and x should be contained in the convex hull of stabilizer states. And now you know that you have some invariance property of your linear function a. Suppose a is invariant under some subgroup of the symmetry group of all stabilizer states that we know right now. So this means g of a is a, and if I take the set of stabilizer states, so the polytope or the vertices, then kind of they are preserved under G for all small g contained in the group capital G. Then I can do a trick that is very, very common in convex optimization. So if I have some optimal solution x star for this optimization problem, then I can average this, so I can consider the orbit of x star under the group action here, and I average here. Then this will also be an optimal solution for this optimization problem. And the big advantage in this case is that this group average will also be contained in the stabilizer polytope, but it will also be contained in a polytope that might have like way smaller dimension of the stabilizer polytope. So in this way, so if you understand like how this polytope looks like, you can really reduce the dimension of your optimization problem. And this is really something that people usually do in optimization. They try to identify symmetries of your problem in order to decrease the dimension and to make it more tractable for a computer. And yeah, such a technique was applied to the robustness of magic by Marcus and David. So there they didn't consider the stabilizer polytope, but yeah, I think a version or a set that had the same symmetries. Yeah, you can also, yeah, you can also do it. You can also like consider like more general problems here. This was just an example. Yeah, and takeaway problem here is, are there any problems where symmetries might help to simplify them? Good. Yeah, with this, I'm almost done. So here's some takeaway problems. So first of all, broad message, try to find problems where symmetries of stabilizer states can help. For example, what we have discussed, find a vertex of the lambda polytope such that L alpha yields an unknown vertex when L is a symmetry of the set of stabilizer states. Or find other interesting optimization problems that have some relevance to quantum information and quantum computation and have some stabilizer symmetry. And then there's a more vague thing. I'm not super convinced that this might help, but still I'd like to mention it here. Can these symmetries that we've seen help to tackle like mutually unbiased basis existence questions? So what's this question? So we've already seen what mutually unbiased bases are. We've seen that stabilizer states are D+1 mutually unbiased bases in prime power dimension. But in general, what people conjecture is that there exist strictly less than D+1 mutually unbiased bases in non-prime power dimensions. And yeah, what you can do is you can also see this as a geometric problem. So whenever you have like D+1 maps, they form a polytope, which is sometimes in the literature also known as the complementarity polytope. And the question is, okay, does this polytope live in this quantum state space? And whenever you have this polytope, then a result tells you more or less how the linear symmetry of this polytope looks like. And can you exploit this fact to prove these type of non-existence results? So I'm not sure if this works. I don't really try it, but yeah, I wanted to mention it here. Yeah, and maybe as a last point, I hope I motivated you to study symmetries, to get to know the symmetries of objects. Knowing them and exploiting them can really help and make life much easier. So yeah, with this, I'd like to thank you, and yeah, I'm happy to take any questions if there are any questions.
Thank you, Arne.
Okay, I have a question. So the transposition part of the symmetries, so I'm not sure how they, okay, so if you consider the action on the lambda polytopes, usually we consider the Clifford symmetries, and under those symmetries, the number of the vertices break into small number of orbits, right?
Exactly, yeah.
For this, if you add the transpositions, do they really shrink further, or does it really stay the same? Like, what would you expect?
Yeah, I think I've even like investigated in this, and I think they stay the same because like, so usually what's important are so the expansion coefficients in the Pauli basis. And now if you consider transposition, what does it do? It just flips like y to minus y.
Oh, okay.
And this doesn't give you an extra vertex. Exactly. And we also studied how these like generalized symmetries act on qudit CNC operators. And there we didn't get more as well, I think.
Okay, I see.
Yeah, I don't know the answer, but in particular for qubits, I think my gut feeling would be you go get finer orbits for for like the actions on single objects. Maybe if you look at, I don't know, two-wise transitivity or something, you know, maybe then you get more pairs or something. And for qudits, maybe there's more, right? Maybe you get actually something new. Also with the similitudes, that's right, because for qubits you have like commutativity or non-commutativity, but for qudits there's different ways of non-commutativity, right? If two Paulis do not commute, then, you know, if you anti-commute them, there's a power in the exponent. And the similitudes, they permute this. They can map two pairs onto each other if they differ in the power of the dth root of unity. And this you can't do unitarily. So I think for qudits you have a better chance of cutting down on orbits, but of course I don't know. All of these questions are difficult.
Okay. The problem is even for two qudits, we don't even have a full list of all vertices. I think that when we ran some numerics as like lists with like several thousand of vertices, but these lists are not necessarily expensive. So maybe it could help here.
Okay.
Maybe I can also give an answer to this question about the symmetry group of the phase lattice and this common symmetry group of stabilizer symmetries. So what we've actually shown is that the symmetry group of the stabilizer polytope for multiple qudits is isomorphic to the symmetry group of sublattice of the phase lattice of the stabilizer polytope. So that's the result that we have.
Also, does this imply that the combinatorial automorphism is the same as the linear one? Because
now I think that it's, I mean, I haven't proven it, but probably like the symmetry group or a combinatorial, like when I say symmetry group of the phase lattice, that's like the same as combinatorial, of course. So since it's only like the combinatorial symmetry group of a sublattice, it's probably a smaller.
Oh, okay. So you look at the sublattice. Okay.
Yeah, I mean, if you want more information about the sublattice, it's essentially just like applying co-isotropic subspaces. But maybe there's a bit more details about this.
Okay. Okay. So is this also in the paper joined with David or?
No, like this is a completely separate proof of the same result, which is way longer than the one which we did in the paper. So we decided.
Sorry, I think the sound is a bit not stable.
Yeah, I can comment on this. So it's kind of a result in Valentin's master thesis how you can also derive the symmetries of n-qudit stabilizer states. But as far as I remember, there's one drawback. So we studied certain symmetries of the phase lattice, but however, we required that these symmetries are like inner product preserving, which is kind of a thing that you don't have if you study combinatorial symmetries. So this might be some drawback here, but I'm not completely sure.
Oh, you had more restrictions on the symmetries while you okay.
Exactly, we showed that like certain phases have to be preserved, but kind of the key point here was that we required we kind of as an extra condition we said, okay, inner products have to be preserved as well, and usually if you consider like combinatorial symmetries of a phase lattice, then all you need is that dimension is preserved. So the levels of your Hasse diagram on a high level, but yeah.
Okay.
But yeah, it's a super nice question, in fact, yeah.
Oh, okay. Maybe there are other questions from the audience. Okay, maybe if not, then we should thank Arne again for this very interesting result. Thank you, Arne, for the nice talk.
Thank you. Okay, I will. Yeah,
we should stop the recording, I guess.
Yeah,